Hello, welcome back. Now we're going to talk about loudness, how loud a sound can be. And we call that intensity. Intensity is objective, loudness is subjective. How loud is that? Well, is it loud or is it soft? Intensity is the objective measure of loudness, how loud something actually is. And the intensity is proportional to the square of the amplitude. So the greater the amplitude, the greater the force of the vibration, the greater the intensity of the sound. And the unit that we use for intensity is the decibel, named after Alexander Graham Bell. Deci for it's a base 10, and bell for Graham Bell. Okay, so you have a system that can read loudness, and it's basically measuring the amplitude or the intensity of the sound. All right. Now, starting with 0, and 0 is what the threshold of hearing is. So we say 0 decibels is the threshold of hearing, when you can just barely hear it. And every 10 decibels means that it is increased by a factor of 10. So a sound of 10 decibels is 10 times as intense as 0. 20 decibels is 100-fold because it's a log scale. Um, 30 decibels would be, uh, so basically every 10 is 10 times stronger. So 30 decibels would be 1,000 times louder than 0. 40, 60 would be uh, 10 to the sixth louder, or a million times louder than the threshold of hearing. Which I want you to take that in for a second. The reason we use a log scale, which is like every 10 it goes up by 10, so 20 decibels is 100 times louder, not 20 times louder. The reason we do that is the humans have an amazingly large range of loudness that we can hear or discern amongst. We can really tell loudness pretty well. So what do you need to know? You need to know decibel is the unit. You need to know that 0 decibels is the softest sound we can hear. That's the threshold of hearing. So, threshold of hearing. But that threshold that's loudness. Decibels is loudness. What about intensity? Well, there's actually an equation for intensity that I'm going to get to. But let me do this first, just so you understand. 0 decibels threshold. This talking that I'm doing right here, probably I'm talking a little loud, probably between 60 and 70 decibels is what I'm talking into this microphone. If you're at a rock concert, and sadly a lot of churches I've been at have sound that gets between 110 and 120 decibels. And that's loud. That's really bad. Anything over 100 decibels is starting to damage your hearing. And at 140 decibels and above, you're actually starting to cause pain. Now what this is, we have this equation for decibels, and I'm not going to make you know this equation for the test. I just want to explain something to you. It's a base 10 scale, so it's log 10. It's a log scale. But what this means is it's a ratio of the intensity of sound as it is to a base. And this base could be the threshold of hearing. And your threshold of hearing is actually 1 times 10 to the negative 12th watts per meter squared. That's a watt is a unit of energy per unit time, and this is a very low value. So we can hear things at a very low level. And as it goes up, we take the log of that ratio times 10, and that's what gives us the decibel. So there's actually an equation that can convert that intensity into the decibel. So the decibel is what we use to indicate it, but it's because of this log scale that we use that 20 is actually 10 times louder than 10 and 100 times louder than 0. Every 10 is an extra factor of 10. So hearing damage begins at 85 decibels. Like I said, around that 90, you start to get hearing damage, but that's like long exposure. At around 120 decibels, it takes very little exposure to start to cause hearing damage. So what is the difference between intensity and loudness? Intensity is objective, loudness is subjective. Now, when any object composed of an elastic material is disturbed, it vibrates at a special frequency. We call that its natural frequency. And you guys know this from a tuning fork. Tuning forks have natural frequencies. So we speak of an object's natural frequency. That's the frequency at which an object vibrates when it is disturbed. Bells have natural frequencies. If you've ever been on campus, you know they have two carillons that play songs pretty much every hour using many different bells. The natural frequency is the one at which minimum energy is required to produce the vibrations. So it takes the least amount of energy for that vibration to continue. So that's the vibration that it naturally goes to. Most things have natural vibrations, even your body. So what happens when an elastic material is disturbed? It tends to make the sound at that natural frequency. Okay. Now that's the natural. What about forced vibrations? Sounding boards are an important part of all stringed instruments, right? Because they are forced into vibration to produce a sound. A forced vibration occurs when an object is made to vibrate by first vibrating another object nearby. Okay? So I take a tuning fork and I strike it and it makes a sound. That's the natural vibration. And I'll demonstrate this in my resonance chamber. So I'll do a tuning fork resonance chamber video, or I'll upload one. Okay. What happens is the tuning fork has its natural frequency. I put the tuning fork into a wooden box. And what that tuning fork will do is it will transmit its energy to the box, which will create a forced vibration in the box, which will make the box make a sound. That's a forced vibration. The vibration of guitar strings would be faint if all I had was the string. That's the natural vibration. The forced vibration is the air vibrating within the chamber that allow us to hear the sound. Without that music box, the sound is barely audible. Play an electric guitar without it being plugged in, for instance. Okay. So why are sounding boards an important part of stringed instruments? Because the natural vibration may not be loud. A bell, it's loud, but for a string, it's not as loud. By creating a forced vibration by using a resonance chamber, you can increase the amplitude or the volume of that sound. Okay. And that's where we get to resonance. An object resonates when there is a force to pull it back to its starting position and enough energy to keep it vibrating. Now that's what that means, but let's look at this. Let's try to explain it in examples. If the frequency of a forced vibration matches an object's natural frequency, resonance happens. So I am forcing you to vibrate at the same vibration that you want to vibrate. So let's say that I have a guitar and that guitar string vibrates at a natural frequency. I could put that guitar string over any sized box and it will create a forced vibration and I'll be able to hear it. But what if I use a box where the natural vibration of that box, the natural frequency of the box, equals the forced vibration that's being put into it? So the natural vibration of the box equals the natural vibration of the string. So I hit the string and it transfers its energy to the box, which is also the natural frequency, and that's when we get resonance, which is an increase in the sound volume, right? Like when you're pumping on a swing. If I pump on the swing at the same frequency that the swing is spinning, so the swing is spinning and I am inputting energy at the same frequency as I keep saying spinning, but swinging, then it will swing higher. That's an example of resonance. It has to do with timing. It has to do with natural frequencies. If I have two tuning forks that have the same frequency and I hit them both, I will get a louder sound. I can even hit one tuning fork and put another tuning fork beside it, and if they have the same natural frequency, the energy will actually transmit from one tuning fork and start the other tuning fork vibrating. So it can actually transmit. So here's a tuning fork. A first compression gives the fork a tiny push. The fork bends. The fork returns to its initial position, and you'll see that the sound wave is actually moved from one side to the other. So that's an example of resonance. If I have one tuning fork and another tuning fork, and they're both the same, one tuning fork creates a sound. As that sound hits the other tuning fork, it's at the same vibrating frequency as the fork. So it causes a resonance. And if they don't match, then it's bad. Now, an example of when resonance goes bad, and I'm going to do bridge collapse, so I'll make sure I add that video too. What happens if you have a bridge and wind is blowing that bridge? The bridge has a natural frequency. What happens if the wind blowing has the same frequency as the bridge? And what happens is you get something famous like the Tacoma Narrows Bridge. This bridge literally gets ripped apart by resonance because the vibration, the natural vibration of the bridge equaled the wind that was blowing through that. And it actually caused a major change in bridge design after that. So what causes resonance? When the natural frequency is equal to the forced frequency, the forced vibration. That's one way to put it. And we've already talked about interference. So I'm not going to go through it too much here because that was in the last chapter. But here are two waves that have the same frequency, so you get amplification or reinforcement. Here you have sound, so longitudinal waves, and you get reinforcement. But if I go back to the sound, if the compression and the rarefaction do not match up, the sound goes away and they destroy each other. Destructive interference, constructive interference. Now I told you before that depends upon that the waves arrive in phase. Notice how these speakers are the same distance from the viewer. So the waves both hit the viewer at the same point. They're both at compressions. Now what if I move one of the speakers? So B, the speaker right by the B got moved farther out, or no, actually, this one got moved farther out. So now I have 1, 2, 3, 4, 5 waves. Here I had 1, 2, 3, 4, but the fifth wave hit right on the person. But here the fifth wave is out of sync. These are out of phase. The rarefaction from this speaker, from the right speaker, equals the compression of the left speaker. So if they're out of phase, we get destructive interference. So what are the effects of constructive and destructive interference? If it's constructive, the amplitude increases. If it's destructive, it decreases. Okay. So I'm going to save the beats, and really we just have a couple more things, but I'm going to do beats separately and then we'll do, just because we're at 12 minutes, I might as well stop and then start another video.